In 1965, a young Caltech graduate student by the name of Gary Flandreau was poring over his notes in Building 180 of the Jet Propulsion Laboratory, studying the intricacies of using planets' gravitational fields to slingshot spacecraft into the outer reaches of space with no need for additional propellant. The gravity assist, a method of propulsion that uses the gravity of a gravitational body to literally pull the spacecraft into a new trajectory and velocity. As he examined the possible trajectories, Gary noticed something incredible. In the late 70s, a window would open up where the alignment of the planets would allow for a single satellite to pinball its way between Jupiter, Saturn, Uranus, and Neptune, before eventually being spit out to the outer reaches of our solar system and beyond. With this knowledge, a flurry of activity began within NASA and JPL. A once-in-a-lifetime opportunity had been found that would not come about again for another 175 years. And it was imperative that the opportunity was not squandered. Planning began, and in 1977, two satellites, Voyager 1 and 2, would launch aboard the three-staged Titan IIIe rocket. Voyager 2 would utilize a gravity assist with Jupiter, Saturn, and Uranus before racing by Neptune, before it eventually exited the solar system, while Voyager 1 completed a more direct path, whipping by Jupiter and Saturn before venturing into deep space, moving away from Earth faster than any other spacecraft. Voyager 1 is now over 22.8 billion kilometers away from Earth. That's so far away that Voyager 1 is now outside the influence of the Sun's constant stream of solar wind, meaning it is now in interstellar space, officially reaching the region in August 2012. We, as a species, have now left our mark in interstellar space after a 35-year-long journey, a ponderously long time in the scale of human life, and that was with the help of multiple gravity assists. While we can build and deploy these technical marvels to investigate other worlds, sending ourselves into space is another thing entirely, and using gravity assists to visit our closest neighbours makes little sense. To date, the furthest humans have ventured into space is to the dark side of the moon, a mere 400,000 kilometers away. If our ambitions to create colonies on Mars are to be realized, humans are going to need a spacecraft that are faster and more efficient than the ones we currently have at our disposal. Mars is on average about 64 million kilometers away. The fastest and most efficient method we have to reach Mars using the Hohmann transfer method, with launch windows every 26 months, takes about 9 months to complete. Faster transfer times are possible, but engineers are stuck in a catch-22. It takes fuel not only to accelerate the spacecraft, but to decelerate it too. There are no disc brakes in space. The more we accelerate, the more we have to decelerate too. In order to carry all that additional propellant, engineers will be forced to sacrifice payload weight, reducing the space available for food, water, and other vital supplies for a crewed mission to Mars. We can take some solace in the fact faster transfer times will reduce the supplies needed and will reduce the crew's exposure to the high radiation of space. But what if we could achieve faster transfer times without sacrificing payload? What if we could achieve faster transfer times with even more payload? Let's first examine current technology to see where things could be improved. The Atlas V rocket that brought Perseverance to Mars utilized chemical combustion to propel itself, a method where a fuel and an oxidizer are combined in a combustion chamber and ignited. The resulting exothermic reaction causes the combustion products to rapidly heat up and expand. The nozzle design then directs the expanding gas in one direction to achieve thrust. Getting the most out of our fuel and oxidizer is the first step to maximizing our thrust per unit weight of fuel. There is a useful quantity engineers use to describe this property of fuels and oxidizers, specific impulse. We described in detail what this value represents in our last video on the X15, explaining how it represents the total energy we can extract from our propellants per unit weight. In that video, we used this equation where specific impulse is defined by thrust force divided by fuel flow rate. This is an extremely important metric for our Mars transfer vehicle. The higher we can push our specific impulse, the less fuel we need to bring, which frees up space for payload. Or we can bring the same amount of fuel and increase our velocity to reach Mars sooner, or even be able to leave outside that ideal Hohmann transfer window. So, how do we improve specific impulse? The technology with the best specific impulse currently is ion propulsion. Take the N-Star ion drive aboard the now retired Dawn spacecraft. This engine used electric power to propel ions and achieve astronomical specific impulses. The engine releases xenon atoms into an ionization chamber and then bombards them with high-energy electrons. The collisions produce a positive xenon atom and more electrons. These electrons are then collected by a positively charged chamber wall, while the positive xenon atoms migrate towards the chamber exit, which contains two grids, a positive grid called the screen grid and a negative grid called the accelerator grid. The high electrical potential between these grids causes the positive ions to accelerate and shoot out of the engine at speeds of up to 40 kilometers per second, which is vastly higher than what chemical combustion can provide, which has a typical exhaust velocity of about 3 to 4 kilometers per second. This exhaust velocity is paramount to achieving higher specific impulses. If we play around with the specific impulse equation, we can see why. Specific impulse equals the thrust force divided by fuel flow rate. Thrust force is equal to the mass flow rate times the velocity, while the fuel flow rate is the weight of the fuel on Earth, and thus this value changes to mass flow rate times acceleration due to gravity. And, as we see, the mass flow rates cancel themselves out, leaving us with only exhaust velocity divided by gravity. So, it's rather obvious. To maximize specific impulse, we need to maximize exhaust velocity, and ion propulsion is the best technology we have to do that right now. With 10 times the exhaust velocity, the ion drive can achieve 10 times the specific impulse. That's a phenomenal increase. So why aren't we using this technology for interplanetary missions? Mass flow rate may not be important to specific impulse, but it is massively important to thrust. As we saw just now, thrust force is equal to mass flow rate times the velocity. Chemical combustion happens extremely quickly. It is, after all, a controlled explosion, and so it is capable of accelerating millions upon millions of molecules out in a very short space of time, leading to a high mass flow rate. High thrust is very important for particular maneuvers, like capture burns, where a rocket will fire to slow its speed down enough to be captured by a planet's gravity. The window for this deceleration may only be a few hours, where ion propulsion simply cannot provide enough thrust in a short enough time to successfully complete the maneuver. Ion propulsion simply does not have the mass flow rate necessary to achieve high thrust. It took the Dawn spacecraft 4 days to change its velocity by just 94 kilometers per hour. To increase our ability to change velocity quickly, we need to increase the mass flow rate. To do this, we need to increase our input power. For ion propulsion, that power comes in the form of electricity, which provides the energy to ionize our propellant and accelerate it using an electric or magnetic field. Current generation ion-propelled spacecraft use solar panels to provide that electricity. The Dawn spacecraft has panels capable of producing 10 kilowatts of power when orbiting Earth, which diminished to 1.3 kilowatts by the time it reached its destination in the asteroid belt 3 times further away from the Sun. Scaling that solar power becomes impractical very quickly. NASA estimates that a Mars transport vehicle would need at least 400 to 2,000 kilowatts of power to carry astronauts and cargo to and from Mars. So, how do we power something like that?